So we wrapped up the last lesson talking about special triangles, special right triangles, and we looked at two specifically. We looked at the 45-45-90 triangle, and then we looked at the 30-60-90 triangle. And we found with those special right triangles that they have specific ratios between their sides all the time. So every 30-60-90 triangle, based on the angle-angle theorem, means that they're similar. So every 30-60-90 triangle that we come across is similar to every other one. And because of that similarity, there's always the same ratio between their sides. And so we found with 30-60-90 that if we're looking at the short leg and the hypotenuse and the long leg, we have a ratio of 1 to 2 to the square root of 3, always. So even if you have one that's bigger, notice this one's definitely bigger than this one, but it's still a 30-60-90 triangle, and so we still have that proportion of 1 to 2 to the square root of 3. So the hypotenuse is twice the shorter leg, and the longer leg is the square root of 3 times the shorter leg. And we're always going to have that. For every single 30-60-90 triangle, we have these nice whole number, well, I guess root 3 is irrational, but we have this nice pattern to follow. Now, we looked at 30-60-90 triangles, we looked at 45-45-90 triangles, because those are often used. They're very popular types of triangles. They're used in a lot of problems. They're very handy to know. But really, we can do this for any triangle. So for example, if we look down here, we've got a 189-90 triangle, if you want to say that. Right? Much different than what we have up here. Not one that you come across very often with a 1-degree angle. Right? This is, like a sliver. So if we look at this situation, though, we have another kind of triangle, and if we consider this angle of 1, this type of triangle would still have the same proportions. So if we look at a smaller version that has the same angles, again, angle-angle postulate or angle-angle theorem would say that these two are similar, and so they must have the same proportions. And we can look at their proportions just like we can look at this and say, the short leg to the hypotenuse is a 1 to 2 ratio. In this 30-60-90 triangle, in this 30-60-90 triangle, still 1 to 2 ratio. We can do the same thing with a 189-90 triangle. It's just not, we don't memorize it, we don't learn about it specifically because it's not one that we use all the time. So essentially, we could look at the short leg here and the long leg here, and we could conclude that the ratio of the short leg to the long leg in this 189-90 triangle is going to be the same as the ratio of the short leg to the long leg, so C over D, of this other 189-90 triangle. And any 189-90 triangle, whether it's this big, or bigger than the page, are going to have the same ratio when we divide the short leg and the long leg, right? So the neat thing is that really for any kind of triangle, we could find the proportion between the two legs. In this case, remember when we have right triangles, we call this the hypotenuse, and then oftentimes if we're referring specifically to this angle here, we would call side A would be the side opposite of that angle, and side B would be the side adjacent to that angle. So if you think about it that way, A would be the opposite side, B would be the adjacent side. And so for any triangle, we say with a 1-degree right triangle, the ratio of A over B is so much. If we had a 2-degree triangle here, it would be something different for any triangle with those angles, right? No matter how big or small it was, it's going to be similar, and it's going to have the same proportions. And so we could carry around large tables. If we look at this table here, we could carry these tables around with us all over the place, and we could say, okay, if we have an angle of 10, well then we know that, we're looking at A over B here, so the short leg over the long leg, or the opposite over the adjacent side. So if we look at a triangle that has a degree of 10, if we were to take this side and divide it by this side, we would get this value, 0.1763. Alright, got that out of the way now. We can use this to check our standard 30-60-90 triangle. And if this column represents the ratio between the opposite side and the adjacent side, well then if we look for 30 degrees, the value should be 1 divided by the square root of 3. So if we look, the value they have here is 0.5773. And if we pull up our calculator, we can do 1 divided by the square root of 3, and that gives us 0.5773. So this chart basically gives us the ratio between the opposite side and the adjacent side of a triangle with this specific angle. It's got to be a right triangle, but if you look at these angles and you look at the side opposite divided by the side adjacent, you're going to get whatever this value is here. Now, we could carry these around with us at all times, which would be a giant pain in the butt. Instead, our calculators are set up to do this. This value of opposite over adjacent is called the tangent functions. And so if you take your angle, for example, if we take 30 degrees and we click on tan, it gives us that value. So essentially what these tangent, sine, and cosine are the three trig functions we're going to learn. You'll see them on your calculators. I've got them right here. Essentially what they do is they tell us the ratios between certain sides on specific triangles. So, we can say, well, if we have a triangle that has a 59 degree angle, so if I just had some random triangle here, and let's say this was 59 degrees, and I wanted to know the ratio between the opposite side over the adjacent side. So I was trying to find x over y. I would just plug in to my calculator tan of 59 degrees. Punch that into the calculator. Right, 59 degrees tangent, I get 1.644. which we can double check with our table here. 59 degrees, 1.644. Alright, so moving into the actual lesson. Now that we understand what the tangent is. The tangent is really just the ratio between the opposite side and the adjacent side of a right triangle of a specific degree. So, tangent of the acute angle is the ratio of the leg opposite. Get my bigger eraser. To the adjacent. So if we're looking at angle A, then this side here is going to be adjacent. This side over here is opposite to angle A. So the tangent of this, tangent of A, would be opposite, which is BC, over adjacent, which is AC. So the length of the leg opposite, length of the leg adjacent. So you can just write opposite over adjacent. And actually, eventually we'll just write O over A sometimes as well. So let's put this to use. If we look at our example, they want us to write the tangent ratios. So they want us to write it for A and for B. And that's something to keep in mind, is that if we have a right triangle, angle A has a tangent, which is represented by the opposite side over the adjacent side, and angle B has a different tangent represented by the opposite side over the adjacent side. A has its own tangent and B has its own tangent based on the fact that they're on opposite sides of the triangle. So for A, we would do opposite, which would be this side over here, right? That's going to be BC, over adjacent, which is going to be this side here. The adjacent side in this case for angle A is AC. So we just plug in the value for BC, plug in the value for AC, and we get our tangent ratio, 20 over 21. For B, it's going to be different, right? If we look at this angle up here, the opposite is now AC, which is 21, and the adjacent is BC, or 20. So if you notice, when you're looking at a right triangle and you're looking at the two different non-right angles, their tangents are actually reciprocals of each other, because the opposite side to A is actually the adjacent side to B, and the opposite side to B is the adjacent side to A. So these are always going to be reciprocals of each other. couple more examples. If we're going to use this, it says, to measure the height of a tree, Alma walked 125 feet from the tree and measured a 32-degree angle. So there's 32 degrees. From the ground to the top of the tree, estimate the height. So we've got a distance here, and we've got an angle. And we know that the tree, in terms of measuring its height, we always measure at a 90-degree angle, so the tree forms a right angle with the ground. So we can use the tangent in this case. Up to this point, we've always needed, to find this third side, we've always needed either the second side so that we could use Pythagorean theorem, or we needed another triangle over here. You know, we needed some other triangle that was 32 degrees and that had a different value, so we could look at the similarity, right? You know, and say these two triangles are similar, and so we can get some values here. But we don't need that anymore. Now that we have these trig functions, right, we can just say, well, the tangent of 32 degrees, right? Remember, the tangent represents the opposite side, which is going to be the height of the tree, over the adjacent side, which is going to be 125, right? And that's the distance on the bottom. So if we're trying to find height, multiply both sides by 125, we get 125 times the tangent of 32. Remember, this tangent function, we could go back to the chart that we had originally found and look for tangent of 32, but our calculators have those charts programmed into them. So we can just hit in the calculator, clear this out, 32 tangent, we get 0.624 times 125, and there's 78.1, right, which is what they get here. So the tree is about 78 feet tall. So again, punching this into your calculator basically just has your calculator look up for you on this chart what is the ratio of this side to this side, sorry, let me point it out, of the opposite side over the adjacent side in this type of triangle. Because remember, any triangle that's a right triangle that has a 32-degree angle here is going to be similar. So they'll always have the same ratio. Opposite over adjacent will always be the same. Right. We can also do this in reverse. If we know what the ratio is, we can find the angle. So in this case, they give us two sides, and they want us to find R, right? They're trying to have us find this angle up here. Well, if we look at R, the opposite side to R is 47, and the adjacent side to R is 41. So we know that the tangent of R is going to be 47 over 41. And so in order to find the angle this time, see, we're working backwards. Before we had the angle and we wanted to find the ratio. Now we have the ratio, we want to find the angle. So it's really just a reverse lookup. If we did 47 divided by 41, we get 1.1463 and so on. So if we were to look at our chart, we could go and find 1.1463 would be somewhere in here between 55 and 56. Oh, sorry, 1.14. Here we go. Up here, between 48 and 49, 1.14. So we could go to our chart and look this up, but the calculator would do it for us. So if we punch in 1.14, so on, and do the inverse tangent, right? So that's tangent to the -1 is the inverse. You're telling it to do the opposite. So if we were to punch that into the calculator, we would get the inverse tangent, 48.9, just like I said, between 48 and 49. So the angle was about 49, just under 49 degrees. Okay, so we're letting the calculator do that work of looking up these values in the chart. All right, that's it. We're just doing tangent for today. We will introduce sine and cosine at a later time, and we'll use those as well, and we'll find out exactly what those mean. But for right now, let's just make sure that we all understand the relationship between the tangent function and the ratios of the different sides of the triangles.